Hello and welcome to lesson 16 on the chain rule, where today we're looking at our last rule for differentiating functions, and it's actually one of my favorites because it really ties in all the ideas we've been learning so far. So today we're going to learn how to use the chain rule to differentiate composite functions. And specifically as we learn this, I'm going to make a connection with one of the other rules that we've seen before. So first, considering what a composite function is. So a composite function is when you have two functions f and g, and a composite function is written as f with that circle g, and it's pretty much when you have f of g of x. So your input is actually g of x. For example, if we have f of x as the function squared of x and g of x as x plus 3, first let me just write uh, yeah, I'm gonna write this one here, these two, which are the composites. So this one is f of g. So what it means is we're going to have f of x plus 3, which is square root of x plus 3. And the other way is if we have g of f, which is going to now be g of square root of x, and this is now square root of x plus 3. And those are the general forms. And now let's try these two examples. So g of 6 is just 9. So then when we have f of 9, this is just square root of 9, which is 3. And for the second one now, f of 9 is square root of 9. So then we have g of square root of 9, or just 3. And this is g of 3. 3 plus 3 is 6. Okay? So, yeah. So again, it's pretty much when you have a function as an input for another function. And when you have such a function, so we have composite functions, the way we differentiate them is using the chain rule. So the chain rule tells us that if we have two functions, f and g, and each of them have derivatives, so they're differentiable, then the composite function h of x, which is f of g of x, has a derivative given by h prime of x, and you take the derivative of f with respect to the input g of x, and then the derivative of g of x itself, so g prime of x. And the proof of this is a little bit complicated, so please take your time to read through it. But we start with our definition of a derivative, and this part we are assuming that we don't have a zero value there, so we can't actually de find the limit. So that's why we had to have that g of x is also differentiable and has a derivative. And so here we're just using our limit laws to expand this and rewrite it. And we can see that this part over here is going to be equal to f prime of g of x. And this one is g prime of x. Okay, so again, please take some time to look through this, read it. It is not required, but it's helps maybe understand the chain rule a little better, especially with connections to limits, and it can definitely help strengthen your math knowledge by reading through proofs. So moving on, we have our first example. And this is actually exactly what I was referring to at the beginning of this lesson when I said we actually saw a version of the chain rule. And if you remember from power of a function rule, that's pretty much the chain rule. So consider we had f of x is x plus 4 squared. Then now, based on the chain rule, we are finding the derivative of this whole function. So we'll have 2 x plus 4. And in this case, d of x plus 4 by d of x is just 1. And so we do have that 1 there. And it doesn't actually make a difference, but if you had a more complex function inside the bracket, then it would. So let's look at now this example where we have both a more complicated exponent as well as a more complicated function inside the bracket. So here, the inner function is x squared plus x. And so finding the derivative here, we have 2x plus 1. And this is the 2x and this is the 1. Now the outer function, this is actually just x to the power of 3 over 2. And again, we don't look at what's inside the bracket because that's g of x. So we're just looking at the outer function. And now we know by power rule that this is 3 over 2 x. And that's just the takeaway one. But this can also be written as such. Okay, so I'm sticking with this representation for the chain rule. So here, this is just my definition of the chain rule. Now I have that 3 over 2, and now I'm substituting instead of x, g of x, which was x squared plus 1, and I kept that half there as my exponent. And this 2x plus 1 is just the derivative g of x. So this is g prime of x, and this is f prime of g of x. And now you're asked to find the derivative of this other function with the chain rule. And this one I'll actually maybe try it just because it's maybe more difficult concept to start off with. So here, start with your product rule, and we get 3, 5x squared plus 7, 2, right? That's just the product rule for this outer function. And now I look at my inner function, which is 5x squared plus 7, and the derivative of that is just 10x. And that's it. And you can expand this to make it look a little nicer. So we have 30x and then 5x squared plus 7 squared. And there you go. Oh, and I missed that there. And that would be our derivative function for f of x. Now, I'm also going to show you the chain rule with Leibniz notation because this is the one that's going to be different from all the ones you've seen so far because we have different, we're differentiating with respect to different variables. So consider y as a function of u. And so this would be f of x, and this would be g of x, right? And u itself is a function of x, so y is a composite function. So then, when we differentiate y with respect to x, we have to consider that y itself is u is a function of u, which is a function of x. So then, first we have to differentiate y with respect to u, and this is f prime of g of x. And then we have to differentiate u, the inner function, with respect to x, and that's g prime of x. So yes, we do have now another variable in our denominator for the Leibniz notation, and this is the case for composite functions. And this is only true provided that this derivative itself exists. Oh, sorry, there should be, I'll add this, both of these derivatives need to exist, right? Same with our Lagrange notation. We need both g prime of x to exist and f prime of g of x to exist as well. So now let's practice that with Leibniz notation. Oh, so consider here we have y and we have u here. And we're asked to find the derivative at x is equal to 4. So starting with the chain rule, uh, and I'm using Leibniz notation, so good practice here. We are differentiating d of y by d of x with respect to x, but chain rule tells me that I need to split this into two parts. So first, I'm going to differentiate d of y with respect to u, and then I'm going to differentiate u with respect to x. And clearly here you can see the input variable here is x and the input variable here is u. And that's why we have the different, or differentiating with respect to different variables. So in the first part, here I have a power rule, which gives me 3u squared and minus 2. And the 1 is just a constant. And in the second part, this is similar to above. This is 2x to the power of half. And if I differentiate this, I actually end up with just 1 over square root of x. But here I now have two variables, u and x, which I don't want this. We need to have one variable. So then, and exactly that's, so in this case, because we have to find it at x equals 4, that's actually now my question. Do we need to expand it fully in terms of x to find the derivative at x is 4? Keep in mind, this is different. If you were asked to find dy of d of x just on its own, then yes, you definitely have to for sure rearrange this or substitute the value of u in there and rewrite this as an expression with just x. But because we have to find the derivative at a specific point, do you think we still need to do that? So let's try it out. We know that when x is 4, u is 2 times square root of 4, which is just 4. So let's try now. I'm just substituting now. I have my x is 4, and I have u is 4. So I'm just putting those values, substituting those values of x and u. And I will end up with 3 times 4 squared minus 2 and 1 over square root of 4, which is 23. And so no, you don't actually need to expand fully when you're finding the derivative at a specific point. And we've seen this in previous examples as well, where I told you when you have more complex expressions here and you have to find the slope at a specific point, it's not necessary to expand it. But again, if you were asked to find the derivative, then the derivative function, then yes, you do need to substitute for so that your final answer is only in terms of x. And another practice question for you, if y is equal to 2u to the power of 4 plus 3u squared, and u is given by square root of x plus x, then find the derivative at x is equal to 1. Now, our next example that we're going to be doing in our lesson, you're asked to differentiate now h of x. And this is now a mix of product rule and chain rule. Because as you can see, I have two products, but within each of those, I also have an inner function there. So f of x being x squared plus 1 to the power of 3, and g of x being x plus 5 squared. So first we're applying the product rule. And here I just rewrote the product rule as f prime of x times g of x plus g of x times f prime of x. But we need to find now that, oh, my bad. This should be g prime of x, and then just over here. I'll edit this for you guys, but there. Because we need the derivative for each of those. But here, to find f prime of x, we have an inner function. And same with this one, we have an inner function. So here now we're going to apply the chain rule. So the inner function being x squared plus 1 and the outer function being x cubed, then by the chain rule, first I start with this part. So 3, which is my power, and then just I keep the inner function as is, and now this is 3 minus 1, which is power rule. And then this 2x comes from x squared plus 1. And if we now expand this, we have 6x times x squared plus 1 squared. So if you remember, this is actually just the power of a function rule. But that actually comes from chain rule. So I did introduce the power of function rule to you so you can get started on working with derivatives of certain polynomials, but it actually just is one of the components of chain rule itself. And so we can see that whether you think of it as power of function rule or the chain rule, you will still get the same answer. And same thing with g of x now. We apply the chain rule, and our inner function is x plus 5, and our outer function is x squared. So by chain rule or by power of a function rule, we have 2, x plus 5, and then 1 is just the derivative of x plus 5, and we have 2 times x plus 5. And now, putting it all together, I just substituted those values in. And again, you can work on making this look a little bit nicer. Possibly, I could see that I have these two terms. So this and this I can factor out, as well as this and this. And you can try factoring those out, but this would be sufficient to write as well. And again, if you're working for finding the derivative at a specific point, and you can just work with that expression right there and substitute your values in. Now let's try another real life application, and this time we have volume. So the formula for the volume of a cube in terms of its side length, S, is, is expressed in the terms of a variable x. So the volume of S itself is S cubed, we know, but the side length is expressed in terms of a variable x. So S itself is going to be 3x squared minus fx plus 1. So now, I'm sure you can see that V is 3x squared minus 7x plus 1 cubed, which is a composite function. And so we are using the chain rule to differentiate. And one last detail, we're asked to find the derivative of the volume with respect to x at x is equal to 3. So using chain rule, d of v by d of x is given by d of v by d of s because v is has an input variable of s, and then d of s by d of x because s has an input variable of x. So here, d of v by d of s is just 3s s squared. And d of s by d of x, which is the derivative of this internal function, so 3x squared minus fx plus 1, is 6x minus 7. And now, again, because we are asked to find the value at x is 3, I can just, I know x is 3, and then s of 3 is and this will be 7. So now that's where I have x is 3 and s is equal to 7. And so I don't actually have to go back and substitute it here, because I have those two values. So I'll just work with what I have here. So there, s squared will give me 49, and 6x minus 7 will give me 11 there. And if you multiply this, you will end up with 1,617. And I'm missing my units there, but we should have So volume is centimeter cubed, and then the side length is centimeter, so centimeter squared. Okay, and yes, so there's that connection there now with power of a function rule. So we had seen it before, so now we're just making that connection that this is the same as the chain rule, where our outer function is um, x to the power of n, and our inner function being g of x. So then by the, so f of x is xn. So then by power rule, we have n x n minus 1. And then because of chain rule, we have to uh, have our input as g of x, and then also find the derivative of g of x. So now let's apply that. We're asked to find the derivative of g of x, which is given by 1 plus x squared over 1 minus x squared to the power of 10. So first we're going to distribute the exponent here, and, we have our numerator as 1 plus x squared 10, and our denominator is now going to be written as a negative exponent, so 1 minus x squared to the power of negative 10. And here we're applying a mix of product and chain rule, and I won't go over every step of this, so please make sure you're going through to read and see how I get each step. But I keep applying the product and chain rule to get our final answer here.